Welcome back. Today I will talk you through the implementation of a principal component analysis using Python and also using Scikit-Learn. I won't type the code because first of all that is not really my code. Number two, it takes forever to type. And number three, I want to show you the skill of reading someone else's code, because you can learn a lot from that and you can also use some of the ideas in your own coding. So first you note that there is a large list of libraries we import. All of them you already know. We talked about pandas, we talked about scikit-learn, obviously NumPy, we used it many times, and then matplotlib for plotting our series or data. Then we load data, and again you see this is a pandas implementation. We read a CSV file, and that is located on the website. So actually this is an online data source which we load directly online. And we remove the headers, which we replace using our own headers in the next line. Now again, I don't really discuss the data here because it doesn't really matter to us. It's a data on wine. This is all we need to know. Let me just run the first part and let's see how that works. And as you can observe in our variable explorer, we have now the data frame. In pandas we have the class labels, so again these are our labels. We observe we have three distinct labels, and then we have a large number of covariates, quite a large number of covariates. Now that means we can now use all of these variables to try to understand the labels in our training data set. And now we actually follow the same steps we have done before. So I will go through this a little bit more quickly. Number one, we specify our target variable. And you can see here one way of implementing that, which simply refers to our df_wine, which is our data frame, and then it uses the ilog. Now the ilog is basically an indexing method which you can use in a pandas data frame, which allows me to index, to slice, as you're used to in the case of lists. So what that actually means is I go into my pandas data frame, I look at the index location, I take all the rows, that's the first entry, and the column simply means I take all the rows, and then I refer to column 0. Again, of course, you know that Python counts from 0. So that basically means looking at my data frame, I go into the class label. Yeah, so I focus on the first column here. The index is not a column, it's an index. Good. The alternative way, which of course works quite well as we have used it before, is to refer to the actual class label which we specified in line 27. So that would also work. It will give you a pandas series which can be used in a similar way. Then for our covariates, we simply take all the variables. So put differently, we start at column position 1 and we go to the end. And again, this is a typical slicing notation which we have used several times before. So when we run all of that, we should be able now to see our data matrix. So that's the data matrix here, and our target variable which refers to our labels. So that looks all as you would expect. Now the values attribute basically would focus on the actual values stored in the pandas data frame, and what you obtain is you obtain then the values presented as an array. But again, this is an optional way of doing it. There are other ways to handle it. You can go into a series that would also work, so it's a matter of choice. This specification works later better for our work in NumPy. NumPy quite likes arrays, but there are different ways of converting this type of data. But using the .values attribute is a convenient way to get my data in an array, which I can then work on in the NumPy library. Now, as we have done this several times, we now split our sample using the built-in train test split function. I suggest to use again a 70% training data and 30% test data, and we stratify, which means we have the same proportion of labels in the training and test data. As discussed before, there are issues with it because of course we make here the implicit assumption that both data sets are similar to some extent, which might not be true. Next, we standardize, and again we have done that before, so I just talk about this very briefly. So we introduce here our SC. The SC is initialized as a standard scalar, which is an object defined in Scikit-Learn. Now, based on my object SC, I use a fit transform, which is a method in the class standard scalar. I pass my training data and I observe the data here, and I fit the data, which means I define the mean and the standard deviation. I take the mean and subtract it from my training data, and I divide here by the standard deviation. And this I then call a standardized data set for the training data set. Now for the test data, I also transform, but I use the fitted data from before. Yeah, so that's here the approach, which again we discussed before. It implies, of course, that the training data and the test data are somewhat very similar. They have similar characteristics. Okay, next we now go into the actual methodology of the principal component analysis, which is captured in the lecture in more detail, which we will of course discuss in more detail. So here I only focus on the technical implementation. Now, using NumPy, and there is an alternative, you can go to Scikit-Learn directly, but I now use NumPy to specify the covariance matrix, which you see in line 68. Now that is the covariance based on my training data. What you note is that the training data has been transposed. This is just a technical requirement because the data is presented in a certain format. Because the columns in the original data refer to variables, but in a covariance you actually want to have the variables in the rows. So this is why you need a transpose. And then we use the linear algebra package, which determines numerically the eigenvalues and the eigenvectors. Again, I have a separate session on eigenvalues, eigenvectors, where I explain the concepts in a lot more detail. Now that gives us a list of eigenvalues and eigenvectors. Now let me just try to run this up to this point. So now we have our standardized data, as you would expect, and now we have here printed our eigenvalues, and we start here with the smallest eigenvalue and we go to the largest eigenvalue. Okay, that is quite useful. Now these eigenvalues, they matter. The eigenvalues tell you something about the importance of a principal component. In fact, there is a link between the eigenvalues and the share of the variance explained by a particular principal component. Now next, what we do is we go through these eigenvalues in reverse order. Yeah, so we start with the largest eigenvalue and we go to the smallest, and you see this here in this in fact this is a list comprehension. We have discussed this before, where we sort our eigenvalues according to size, but in reverse order, which means we start with the largest and we go to the smallest. Now the eigenvalues, the eigenvals, as you can see here, are defined as an array. Now you can iterate and sort over an array just like a list. So you can just regard this as a list of different data points. So that also means you can define a loop command. So what you see here is a loop command. So for I in my sorted eigenvalues. So looking at these eigenvalues, what I do is I sort them. Yeah, so I sort them in reverse order, and I go now line by line. I start with the largest eigenvalue, which is then my I, and I divide by tot. Tot is defined as the sum of eigenvalues. Now the sum of eigenvalues, and this goes back to the eigenvalue decomposition, is a measure of variance. So put differently, this expression here, the eigenvalue relative to the total sum of eigenvalues, gives me the share of variance explained by the respective principal component. So that is the idea in this command. So what that will do is, and we just now run this part here, what that will do is we obtain now our variable var underscore exp. So that is our expression here, where we in fact refer to the explained variance. So what I get out of this is I know that the first item, which refers to the first principal component, explains about 37% of my observed variance, the next one about 18%, then about 12%, then 7%, and so on. And you see they rapidly decrease, which is exactly what you would expect. Now the NP cum sum is accumulated summation. So basically what that means is I start, and we can just check that out, I start with the first value in our var underscore exp expression, and I start adding it up. So I start with the point 369, and then I add the next one to it, and so on and so on and so on. So when I look at this expression, I see I obtain, of course, kind of it's like a step function. Yeah, so I obtain values which slowly approach 1, because by construction the total value is the total variance, which is the sum of all of these eigenvalues. So this of course has to approach 1. So that is quite useful. And then what we do here is we simply plot this using bars. So that's the first part here. So that is what is executed in this case. We can just have a little look. So these are the explained components of the variance by the first, second, third, and so on principal component. You see quite a rapid decline. So this is very, very typical. Usually the first 2 or 3 components explain the vast majority of the variance. And then I also plot the step as well. So this is the cumulated sum using the step, which is a step function. And that is a nice illustration where you see that initially you make quite steep jumps. So adding more components really explains an awful lot more. But very quickly, so roughly after about 3 components, the increments are getting very, very small. So again, this means that if I have a high dimensional problem, restricting myself to a few dimensions might be actually quite suitable. Okay, now I just clear the screen here. I delete my data. I just want to start fresh and run all of that and see how that looks like. So now we have this combined figure where we have our accumulated sum of these explained variances for different principal components. We have also the labels nicely shown, and we have this explained as well in the legend. So that is a quite useful figure. Actually, this is publication ready, if you ask me. Good. Now we have done the bulk of the analysis. Next, what we do is we explore the transformation matrix. Yeah, so the idea is now, once we know how many of these principal components we select, we can use these associated eigenvalues and eigenvectors to transform our data. So basically what we do is we do a mapping. So we have a higher dimensional problem. We have many different covariates here, and we plot our data onto a lower dimensional space. And to obtain the transformation matrix, what I need to do is I have to check the eigenvectors linked to my eigenvalues, the ones I use in my principal component analysis. Now what I have done here to simplify this task, just to make things quite easy, because you can easily see things in 2 dimensions, I restrict myself to the 2 most important principal components. And then I check the eigenvalues. So these are the 2 largest eigenvalues and their associated eigenvectors. And what you see here is another list comprehension, where I in fact store the eigenvalue and the associated eigenvector in a tuple going through the list of eigenvalues. Yeah, so that is the idea in this particular case. Yes, I go through the list of eigenvalues. It's actually indexed. Yeah, so you see it's a range command. We used this before. The len command tells me the length of this array. We know it's an array, the eigenvalues. So we start at 0. So we start with the first eigenvalue and then we go further to the next. So that is the idea behind that. Okay, so let me just look at this. First, let's look at the eigenvalues. So these are my eigenvalues. So what I do now is I go through this list step by step, and I put the eigenvalue and the associated eigenvector. Yeah, the eigenvectors are stored again in a different array, and what we do is we just select now the associated eigenvector, which corresponds to the column index. Yeah, so put differently, the first eigenvalue would be the first column in my matrix of eigenvectors, and so on. Then I go to the next column, next column, next column. So this is basically done in this line here. It's a nice application of list comprehension, in fact using a list with tuples, which is a very nice way to store the associated values of the eigenvalue and the eigenvector. So here you have a list now where you have the different tuples, and you see the structure. Yeah, you have here the first eigenvalue and the associated eigenvector, and we are here in 12 dimensions. Yeah, so that's quite useful, good to know. Okay, now the next thing we do is we now start sorting this again in reverse order. So when we do this and we go back to our list, we now have the largest one and the associated eigenvector, and then the second largest, and so on. We only will focus on the first two, so this is position 0 and position 1. So next what we do is we obtain from this expression our transformation matrix W. And what that does is it uses again a very nice way of indexing. Yeah, so let me just illustrate this, and I think that's maybe quite useful if I just illustrate that first. Now we know the eigenvalue pairs and the eigenvector pairs. So eigenpairs is the list with a tuple. Now if I index to 0, when I look into the eigenpairs, it will simply give me the first tuple. Yeah, so if I do that, I will obtain the first tuple, which means I get my eigenvalue and the array, which is the eigenvector. Now if I do the following, I do the index 0, 0, it will refer to my first tuple and the first position in that tuple, which would be, of course, the eigenvalue. Yeah, so 0, 0, when you run this, gives you exactly the eigenvalue. And then obviously 0, 1 gives you the first tuple in the list in eigenpairs and the first position in the tuple. Again, position 0 would be the eigenvalue, position 1 would be the eigenvector. So this will give me the eigenvector. So now I have an eigenvector. In terms of how this eigenvector looks like, in terms of dimension, this is now a row vector. Yeah? The next thing I do is I transform this into a column vector. There are different ways of doing that. One very neat way of doing that is to use the numpy new axis command, and you see that in the second part here. Now what numpy new axis does is it adds one dimension basically, and also this notation here is noted is that we take all these rows and we add one dimension to it. Yeah, so that will give us actually a transpose. So when we run this, you will see this now. You have now a column vector. Again, there are different ways where you could achieve the same outcome, but this is quite a nice illustration of it. So I could, for instance, illustrate that as follows. So if we specify here a variable, say h, and we refer to my first array, you see that this here would have dimension 0. Again, this is something very typical in the setting of Python. It has dimension 0. So if you want to modify this to dimension 1, which is quite often needed in computations, you need to add one dimension. Again, there are different ways of doing that. And one approach here is to use this specification with the new axis. I just maybe define now something. I just call this HH. It's not very good. It's just to illustrate this point. I just want to run this and see what happens. So that's and you see the difference here is I have now one dimension added. Yeah, that has computational benefits. Sometimes if you don't do this, you have to be careful. Sometimes arrays don't match, and you might get mistakes in your computation. But that's just to illustrate what this notation means and how this is related to what we already in fact learned. I think that's quite useful to note. Now the H stack, we know that is a horizontal stack. Yeah, so that I think that shouldn't be difficult. So when we run now all of that and we sort all of it, we should get a useful data matrix. So now that is our data matrix, which has 12 rows and 2 columns. If I use it with 12-dimensional data, I would basically map my 12-dimensional space into 2 dimensions. And that's exactly the idea of the next part of plotting my results. So I take my training data, which is standardized. I use a dot product, which we have discussed before, with the W matrix. So basically I map, so to speak, this 12-dimensional data set into 2 dimensions. So that is exactly happening here, and then I simply plot the data. The rest we have seen this several times before, the scatter plot, there's nothing special about this. Again, you see an application of zip, which we discussed before. That's just purely for illustration purpose to get different colors in my scatter plot. So I will just run that and have a look at the outcome. And now what you observe is if we only have these 2 principal components, you actually get separation. Yeah. So the different labels are grouped nicely together. So it should be possible after the principal component analysis to use now the other methods we discussed, like a logistic regression, to separate these different classes with different labels without the need of higher dimensions. So it greatly simplifies our machine learning algorithm. And in particular, now this is only 12 dimensions, but in real life you might have hundreds and thousands of variables you observe. And then a principal component analysis, a reduction of dimension, is extremely useful. So thank you very much. This is all for today. I'll see you next time.